we go with the Chapter 2 Homework B review. Sorry, I had this title written wrong. It should be in the new system. Chapter 2 Homework B is what we call it now. But the questions are all relevant. And so what I did again was go through Blackboard. This time the average was a little bit lower. It is normal for the homework averages to dip a little bit throughout the semester, so this is still fine. 10.13 out of 12, which is still a little bit higher than last year, so we're ahead of last year's pace by some amount. There were no questions this time that were terribly bad. There were, I think the lowest success rate we had on a question, which I'll go over later, was 43%. Most of the questions we had, the vast majority, we had success rates of above 60% or higher. So it wasn't a single question or single question type that we had trouble with. I think it was just little things here and there that caused the average to be a little bit lower. But I'm going to go through a pretty good selection of topics related to this week's assignment, and some things that I think are going to be relevant for the upcoming exam, and some things that I didn't cover in super great detail in class that hopefully this review will help us clarify a little bit going forward. All right, so we're going to get right into it. So the first one, and there are exam questions like this, so we want to make sure we're familiar with this type of topic, is which equation correctly represents the first electron affinity EA1 of calcium? So a big part of what you have to do, and we'll get some questions like this here, are going to be comparing electron affinities and ionization energies, but we also want to know what they are, what's the precise definition of them. And that's what this question gets after for us, is the definition of electron affinity, in this case for calcium specifically. So what we have to remember is sort of the big distinction between the two is that in electron affinity, we're going to add an electron to the atom. When we're talking about ionization energy, we're talking about removing an electron. And because here we're talking about the first electron affinity, that means it's going to be adding the first electron, adding one electron to the atom. So we're starting with the neutral atom, and the first electron affinity is adding one electron to that. So if we're talking with either first electron affinity or first ionization energy, we're going to start with the neutral atom. And so we can already get rid of choices D and E, because choice D has an anion on the left side of the arrow. Choice E is a cation on the left side of the arrow. And for electron affinity and ionization energy, if we're talking about the first electron affinity or first ionization energy, we need to have just the neutral atom as our starting point, so just calcium. So we can get rid of choices D and E right away, not even to look at them any closer. Now to think about the rest of these, we have to look at which of these deals with adding an electron. And what you can see here is that in choice A, it's going to be calcium plus electron going to calcium minus. And that's exactly what we want for electron affinity. So this is the one we want to pick. Choice B is losing an electron, calcium going to calcium plus electron. This was the answer that most people picked. This actually represents ionization energy. So it is easy to get those two confused, electron affinity, ionization energy. This second one here is ionization energy, but it's not what we're looking for here. This last one here, choice C, is not even balanced. You want to make sure that when you're looking at these, the charge is the same on both sides of the arrow. You're not going to create or destroy electrons in these processes. You're going to just either add them or remove them from the atom, but you're not going to have any net charge that's being created or destroyed. So if we look at choice C here, even though, okay, you're starting with the neutral atom, you're going to an anion, that sounds like electron affinity, but the electron's on the wrong side of the arrow. All right, and the way you can know that is look at, on the left side of the arrow here, there's no charge, just neutral calcium. On the right side of the arrow, there's a -1 and a -2 charge, total of -2. So the charges are imbalanced. So if you're going to add the electron to the atom, it needs to be on the left side of the arrow as it is in choice A. Okay, so there are a few exam questions that you might get one of that's like that, where we ask you to sort of recall the definition of electron affinity, ionization energy, possibly not just the first one, first, second, third, whatever, but the key distinction between them is whether you're adding or subtracting electrons, and that's what we had to look at for this one. All right, so the next question we're going to deal with is classification of elements. So we did talk a little bit about how, based on the location on the periodic table, and in particular the vertical columns on the periodic table, those elements that are related to each other in that way have a lot of relationships to each other in terms of their chemical and physical properties, and that gives them then certain classifications in terms of what we call them, either the big classification being metal versus non-metal, but within those we have some subcategories and things of that sort. All right, so we want to know which of these best describes the set of elements below. We have AS, PB, and HE, so we need to find all of them on the periodic table. Now, as we will see, some of these are a little bit more obvious than others. The one that I think is the easiest to identify is HE. So if we go to the periodic table and find helium, HE, open this up. All right, so this one is over here. It's number 2. It's completely all the way on the right side of the periodic table, so this is clearly a non-metal. Everything on the right is a non-metal, and this last column here being all the way to the right, everything here is a non-metal. We also call these more specifically noble gases. So what we can look at in these answer choices, because that's the one that to me is the most obvious of those three, HE, AS being over here, PB being over here, but we know that helium has to be a non-metal and specifically a noble gas. So if we look at the answer choices here, the last one for HE should be either non-metal or noble gas. And we can see that choice C has metalloid for the last one. HE is clearly not a metalloid. It's not on that borderline between metals and non-metals. So we can get rid of choice C, not have to even think about that one even further. And then choice E has HE as a halogen. Halogen is the group to the left of the noble gases. That would start with fluorine and chlorine and so on. It's clearly not a halogen either. So we can get rid of those two. Then this is how I would approach the problem, is look for those obvious ones first. Now we do have to go through A, B, and D to figure out which one is correct. And again, some of these might be a little bit easier than others to go through. So if we look at choice A classifies arsenic as a transition metal, whereas choices B and D classify it as a metalloid. So let's see which of those is the better choice. Is arsenic AS a transition metal or a metalloid? So what you'll recall is that the transition metals are the ones that are in the D block, this sort of middle part of the periodic table here. Those are all your transition metals. Arsenic is over here. Okay, so arsenic is clearly a metalloid. It's on the borderline between metals and non-metals, which sort of snakes down here as I'm showing. And which metals, which elements are exactly considered metalloids? There's actually a little bit of debate about that, but most of these borderline ones, boron, silicon, germanium, arsenic, antimony, tellurium, polonium, those ones there along the staircase, as we call it, ones that divide the metals from the non-metals. Those are your metalloids. Arsenic is clearly in that middle part, so calling it a metalloid is of course much more appropriate. It's not anywhere close to the transition metals. We can get rid of choice A also. That leaves us to distinguish between B and D. So we have to think of, okay, PB, the last one here, lead, is that a main group metal or is that a transition metal? Okay, and I think this is where there was some confusion. So if we look at PB and go back to the periodic table, PB is over here, lead. Now it's to the left of that imaginary staircase, so it's a metal, but it's not in the middle D block of the periodic table. So lead PB is a P block element, it's a main group element, but it is a metal. So it's what we would call a main group metal, or more specifically if you wanted a P block metal, but it's not a transition metal because it's not, again, in this center part of the periodic table here. Only the elements in the center part of the periodic table are considered transition metals. So of the answer choices that are left, the only one that makes sense would be to classify PB here as a main group metal, which means choice B is the correct one, choice C cannot be. All right, so that one I sort of did by elimination, but again, some classifications are more obvious than others. I think the transition metals are pretty easy to locate because they're in that middle 10 columns of the periodic table. noble gases are very easy to locate because they're all the way on the right, and so on. Some of the categories like metalloid and things are a little bit more tricky to wrap your head around because where exactly is that borderline, where exactly is that cutoff is not always clear. But in this one, I think there's only one answer that is correct for all three choices: metalloid, main group metal, and non-metal. All right, this question I messed up. I forgot to delete part of it. Sorry, I don't know what happened there. This was a carryover from last year's review, which I forgot to get rid of. So anyway, what we're just looking at here is a much simpler question. Forget all these answer choices that I just crossed out. That was from a different question that I decided not to include here. All we're doing is, from the periodic table, choose the larger ionization energy, beryllium or boron, Be or B. So if we go to the periodic table, we will recall that the general trend for increasing ionization energy is going to be bottom to top. So the ionization energy is going to increase as we go up in this direction, and then it's also going to, in general, increase as we go left to right. Now that said, if you go left to right, there are some exceptions in that increasing trend. So what we remember is that group 2, the ionization energies are abnormally large because of the relatively stable P2 configuration. So as you go from group 2 to group 3, the ionization energy actually decreases because of group 2 being abnormally large. And then similarly, group 5 has a relatively stable S2P3 configuration, and so there's a decrease going from group 5 to group 6, again because of group 5 being abnormally large. So you have to remember those breaks in the trend when we're doing this, and that one was especially important here because we're comparing B, E, and B. Now boron B is to the right, but remember that the ionization energies in group 2A are abnormally large. So if we're finding the one that's larger here, it's going to be BE in this case, again because group 2 elements are abnormally large. So think about the trend again, looks something like this, where you have, as you go across the groups, 1, 2, 3, 4, 5, 6, 7, 8, this is ionization energy. There's a general sort of linear increase as you go across. But as you go from group 1 and then group 2 sort of abnormally high off the line, group 3, group 4, group 5 is abnormally high, group 6, group 7, group 8. So they all mostly fall in line. Actually, group 8 is even higher, but that's the highest anyway, so it's off the scale, but it's the furthest to the right also, so there's no exception there. But the point is that group 2 is above the trend, it's abnormally high. Group 5 is above the trend, it's normally high. So as you go from 2 to 3, there's a decrease. As you go from 5 to 6, there's a decrease. You don't typically get a decrease beyond that. So if you compare 5 and 7, 7 would still be higher than 5. You're not going to decrease over 2 groups, just over the 2 consecutive groups. All right, so keep in mind where those breaks in the trend are. In the ionization energy, and then the electron affinity, it's sort of the opposite thing, where in electron affinity the group 2 and group 5 are abnormally low, so it's the same places, just the opposite trend that you have. All right, this question is a conceptual question about energy levels in atoms, and one of the things this requires us to do is know some of the key differences between hydrogen atoms and multi-electron atoms. So let's just go through the answer choices one by one. So in choice A, in high-numbered shells of a multi-electron atom, some subshells of different shells have nearly identical energy. So what exactly is this saying? Well, basically it's saying that as you go to higher and higher energy subshells, when we fill the subshells in atoms doing electron configurations, we're going to go from lowest energy to highest energy subshells. Sorry. What you basically have in this case is, as you go to higher numbered shells, is asking, are there going to be some subshells that have nearly identical energies, and that is certainly going to be true. We're looking for the statement here that is not true, by the way. So choice A is going to be true. As an example, the first place where this really happens, 4s and 3d. So these are two different shells. But anyway, these are 4s and 3d. These are going to be two different shells, different subshells in two different shells, but they're very close in energy. And that's why when we saw there's a couple of exceptions with chromium and copper where it's sometimes possible to promote one electron from 4s to 3d. And it happens a lot further down as well. So, you know, the other, so 5s and 4d and 6s and 5d, and then the, you know, the consecutive F blocks of the 5d and the 4f that are next to each other. Like all these things, and all these higher energy subshells that are next to each other are very close in energy. So that one's certainly going to be true. Now, if we go to choice B here, in the next few deal with differences between hydrogen atoms and multi-electron atoms. Choice B, in a hydrogen atom, all subshells of a given shell have the same energy. So what you'll recall is that the key distinction with hydrogen the energy is proportional to 1 over n squared. And the key point is that it only depends on the quantum number n. So for one electron atom, hydrogen, the energy level only depends on n, which means that all subshells of a given shell have the same energy. So for example, if n equals 3, the 3s, 3p, and 3d subshells in hydrogen are all the same because energy only depends on n, which is the first quantum number. So that one's also going to be true. All right, and this is the key distinction between hydrogen and multi-electron atoms. This is only true in hydrogen where the energy level depends only on n, which means the subshells in a given shell have the same energy. But then choice C, in a multi-electron atom, the various subshells of a given shell have different energies, and this is also going to be true because in multi-electron atoms, it's a more complex relationship. There's not a simple mathematical relationship, but the energy depends on n and L. All right, and so because of this, in a given shell in a multi-electron atom, the different subshells are going to be different. So in the third shell of a multi-electron atom, 3s, 3p, and 3d would be at different energies, and that's why they would get filled in that order. 3s would get filled before 3p, and then 3d wouldn't get filled until after. So these are both true as well. All right, and then if we go to choice D, orbital energies are usually different in multi-electron atoms than the corresponding ones in the hydrogen atom. This one is going to be true as well, and the reason is that orbital energies, remember that they depend on two different things. So they depend on electron-proton attraction and electron-electron repulsion. So in hydrogen, you only have electron-proton attraction because you only have a single electron, so you don't have electron-electron repulsion. In multi-electron atoms, you have both. You have sort of this complex relationship between the attraction between the electrons in the nucleus, as well as the repulsion between the more than one electron that you have, especially the ones that are close to each other in the same shell. And so what that means is that orbital energies in multi-electron atoms are usually different because there's more protons in the nucleus for multi-electron atoms, but then there's also the electron-electron repulsion terms that contribute. And so it's very unlikely that you're going to have the same orbital energy for hydrogen in a multi-electron atom. So the first four of these were true. That means hopefully this last one is not true, or else we messed something up. Choice E, the orbitals within a subshell of a multi-electron atom have different energies. This one's going to be false. So as you'll recall, in a given subshell, all of the orbitals are the same energy. For example, 3p has three identical orbitals three orbitals of the same energy. 3d has 5 orbitals of the same energy, and so on. So with any given subshell, if there's more than one orbital, those orbitals will be at the same energy. So 3p and 3d being the two that will come across the most often in electron configurations. So you have this situation where within a given subshell, the orbitals will all be at the same energies. So this one's going to be one that is false, and so that's the answer that we would pick. All right, so these conceptual questions do require you to go through a lot of times each answer choice and really evaluate all of them carefully to find the one that's correct. All right, there's only a couple electron configuration questions that came up, so we're going to go through 2 of those before we close out. The first one deals with the number of unpaired electrons in the element cobalt, CO. So what we need to do is to find out number of unpaired electrons. There's sort of 2 steps involved. You're going to first look at the electron configuration, and then once you have the electron configuration, you're going to look especially at partially filled subshells and look at those more closely to figure out how many electrons in those partially filled subshells are unpaired. So let's look at cobalt CO and get its electron configuration. We haven't done any electron configuration, so it's good to practice one now. CO is atomic number 27, so if we do the shorthand notation, the noble gas that comes before that is argon, 18. So we're going to put AR in parentheses, 18 core electrons. We have 9 more electrons to add, and if we go to get to CO, which is number 27, we're going to go here. This is the 4s block, so it's going to be 4s1, 4s2. Then we go to 3d, it's going to be 3d, 1, 2, 3, 4, 5, 6, 7. So that takes us to number 27, which is cobalt. So the electron configuration that we get for cobalt is going to be, as we said, argon for the core electrons, 4s2, 3d7, total of 27 electrons. And then if we want to figure out how many unpaired electrons there are, we look at the partially filled subshells. In this case, the only one is 3d. And we need to actually draw out the specific orbitals. So for 3d, there's going to be 5 individual orbitals. As we said in the last problem, these 5 will all be at the same energy. And then to follow Hund's rule, we want to maximize the unpaired electrons and figure out how many there are to be able to answer this question. So if we have 7 electrons to put in there, the way that we're going to arrange them correctly is to start with 1 electron in each orbital first before we pair them up. So we're going to go 1, 2, 3, 4, 5. Then we're going to pair up 2 of them, 6 and 7. And that's going to leave here 3 unpaired electrons. Okay? So with 7d electrons, you're going to have 3 that are unpaired. And so choice D, 3 unpaired electrons, is going to be the one that's correct. Okay. All right. This question here also deals with ionization energy. We talked a little bit about ionization energy earlier. But this one we're going to talk about specifically second ionization energy. So remember that for second ionization energy, we're removing a second electron. So it's going to be a cation that we're starting with, and then removing 1 more electron from that to make a 2+ cation. So for second ionization energy, it's still a gas-phase process, but now we're removing a second electron to make a 2+ cation. And in this case, we're dealing with second ionization energies, and specifically we're comparing aluminum versus magnesium. So when you're talking about second ionization energies, you cannot just use the location on the periodic table. So we have periodic trends for ionization energy, and as we said, ionization energy typically increases bottom to top, increases left to right. There's a lot of exceptions, a couple exceptions anyways, you go left to right. But those periodic trends only work for the first ionization energies, okay? If we're talking about second ionization energy, you need to think about a couple other things. And the first thing you need to think about is the electron configuration of the 2 species that you're considering. So if we're doing the second ionization energy here, in this question we're comparing aluminum and magnesium, Al and Mg. So for aluminum, the second ionization energy is going to be Al plus going to Al2 plus and an electron. And what's helpful to think about is at least the valence electron configurations of these species that are involved. So Al plus, if we go to the periodic table, aluminum is here. The valence configuration is 3s2, 3p1. So Al plus is going to be 3s2. So we've removed the p electron already. For the second ionization energy, we're going to start removing the s electrons. So Al plus has a valence configuration of 3s2. And then we're going to remove one of those s electrons to make a 3s1 configuration. And then if we go to Mg plus, for its second ionization energy is going to be this. So what we have for Mg plus is we will see that in Mg plus, the configuration is going to be 3s1, so Mg is 3s2. We've already removed one. The second ionization is going to start with the 3s1 configuration, and then we're going to remove that last 3s electron to get to the neon configuration. So these are the electron configurations we're considering, 3s1, and then it's going to give us the neon configuration. And I guess if we want to be more complete, these also have the neon core. All right, so these are the electron configurations that are involved in these processes. Again, second ionization is starting with a cation and removing one more electron from that. Now, what you'll see here is the first thing you want to think about when you're comparing ionization energies beyond the first ionization energy, and there's a problem we'll get to later where this is also important. The first thing to think about is, are we going to be removing valence or core electrons? All right. So if you're removing core electrons, you would assume that that ionization process is much harder. In other words, ionization energy is much higher than a process that involves removing valence electrons. But in this case, in all situations, we're removing valence electrons. So in the second ionization energy of aluminum, aluminum has a total of 3 valence electrons. So the second ionization energy still involves removing one of the valence electrons, in this case a 3s. And then for magnesium, which has 2 valence electrons, the second ionization energy still involves removing the last valence electron. So in all these situations, we're removing valence electrons. And so when you're comparing situations where you're removing valence electrons, and especially when those valence electrons are in the same subshells, 3s versus 3s as they are here, valence electrons, they're in the same subshell. The key determining factor in which one is going to be higher is going to be the one that has more protons. All right? Because if you're removing valence electrons and they're all coming out of the same subshell, the one that has more protons in the nucleus is going to hold on to its valence electrons more tightly. So even though the first ionization energies of aluminum and magnesium might behave differently, if we're talking about the second ionization energy here, in both cases, we're removing 3s electrons. Both cases are valence. And so the one that we would expect to be higher is the one that has more protons. If we go to the periodic table, we recall that aluminum is atomic number 13, magnesium is number 12, aluminum has more protons. And so this one here is going to be what we would expect to be higher for aluminum than it is for magnesium. Okay? So the answer that's correct is going to be the one where we have aluminum being higher than magnesium, so we can get rid of a lot of the choices. We also have to make sure we know the reason for that, so that's going to come up as well. So if we look at choice C, that of aluminum is lower. We determine that's going to be wrong because magnesium wants to lose the second electron. So there's not really any such thing as wanting to lose an electron, and that doesn't really come into play here because, again, in both cases, we're removing the same subshell 3s electron. So that one's wrong. That of aluminum is lower because the second electron taken from aluminum is in a p orbital. That's not true. The second electron from aluminum is already in an s orbital, so that one's wrong on both accounts. Choice E, the second ionizations are equal. They don't have the same number of protons, so there's no reason to expect them to be equal. So that one's wrong. And then if we look at choice A and B, both of these have the second ionization energy of aluminum being higher, which is our expectation because it has more protons. We'll see which one has the correct reasoning for that. So that of aluminum is higher than magnesium because Magnesium wants to lose the second electron, so it's easier to take the second electron away. Remember, this doesn't really have anything to do with wanting to lose electrons. Atoms are not sentient beings. They don't have thoughts and opinions about how many electrons they should lose. It's all based on energetics, based on attractions between the electrons and the protons, and electron or electron repulsions come into play at some points. So that one is not a very good explanation for why. If you look at choice B, though, that aluminum is higher than magnesium because the electrons are taken from the same energy level. That is true. They're both coming out of 3s, but the aluminum atom has one more proton. So that's the reasoning that we said is the correct one to think about here, and that's the one that's going to be the correct answer, okay? So aluminum is higher because in both cases we're taking electrons out of 3s, but aluminum has one more proton, 13 versus 12, so we expect it to be more difficult to remove that 3s electron, okay? So, there's some other things that come into play when we're talking about the first ionization energy, and actually the first ionization energy of aluminum would be lower than magnesium, we'd expect. But for second ionization energy, you have to first think about which electrons you're removing, valence or core. If they're both valence electrons, are they coming from the same subshell? They are, and in that case, the number of protons is going to dictate which one is easier or more difficult to remove. Okay, so this question here is also dealing with second ionization energy and asking us to identify the atom that has the largest second ionization energy. So as I said, the first thing you want to do is think about for each of these atoms, are you dealing with valence or core electrons for the second ionization energy? The first ionization energy will always deal with valence electrons because every atom has at least one valence electron. But for these ones, we need to think about, is the second ionization energy, the second electron that comes out, going to be valence or core? So we have magnesium, chlorine, sulfur, calcium, and sodium. So if we look at choice A here, Mg, we just saw it. Mg has two valence electrons. So the second ionization energy would still be removing a valence electron. Same with Ca, which is one of the other answer choices. So those have two valence electrons. So second ionization energy involves removing a second valence electron. And then chlorine and sulfur are two of the other answer choices. This one has 6 valence electrons, it's in group 6. Chlorine has 7 valence electrons, it's in group 7. So they have way more than one valence electron. So the second ionization would still be involving valence electrons for those. So basically these first 4 choices are all valence electrons for the second ionization energy. They all involve removing valence electrons. But then if we look at Na here, we'll notice that Na only has one valence electron. It's in group 1a. So if we're going to do a second ionization of sodium, to remove a second electron requires us to remove one of the core electrons. So the first ionization energy of sodium involves removing its one valence electron, but second ionization would require us to move an electron from the neon core, which is very difficult to do. And so then anytime you're dealing with core electrons, we expect the ionization energy to be much, much higher if it's a core electron versus a valence electron. So in this case, for sodium, removing a core electron, we expect that to be much more difficult, and that makes the ionization energy higher. So if you're looking for the largest one, you're not even comparing all of these in this case, all you have to do, the first thing, as I said, is look at whether it's a valence or a core electron that you're removing. If it's a core electron that's coming out, assume that that one's going to be the highest, because that's always much more difficult to remove than a valence electron. Okay. All right, last one here is dealing with ground state electron configurations. Now, the reason that this one was marked wrong for most of you is not because you didn't know how to do the questions, just because you didn't read the answer choices as closely as you needed to. So we're giving you the partial valence level orbital diagram. So what we'll notice here is that whatever atom we're dealing with has a 2s2, 2p3 valence configuration, 5 valence electrons. So if we go to the periodic table to figure out where that is, 2s2, 2p3, that should be the valence configuration of nitrogen. So nitrogen is the atom that has that configuration. So what most of you did was you just picked choice C here because it has nitrogen in it. That's the full configuration, is helium 2s2, 2p3. Nitrogen is the atom. Most of you just picked this, but you have to look closely because the answer choice also includes the group number. And the group number that's given here for nitrogen is 7A17. Now part of the confusion here might have been the way that we wrote the group numbers here. So if you write it as what we did here was basically, if you write it as 7A with 17 in parentheses, this is just two different ways of writing the group numbers. So this is the one that's marked on your periodic table. We have the A and the B groups. And it's convenient because in the A groups, the group number tells you how many valence electrons there are directly. This is a new numbering scheme, which is not given on our periodic table, but is one that is favored now because there is some confusion with the A's and B's groups, especially the way the B groups are numbered. It's kind of weird. And it's not shown, but basically this new numbering scheme, which is just a number, no letters involved, is going to be where we just number the columns 1 through 18. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, I'm not sure how the lanthanides and actinides, I don't think the lanthanides and actinides have their own group numbers in that numbering system either. But the new numbering system which is what this international union called IUPAC prefers, is just to number the columns 1 through 18 numerically. Now that doesn't tell you anything about valence electrons, so you lose some of that information. But the point is that in this problem we gave you two different group numbering schemes. Now we're not going to try to trick you by having the two numbering schemes not match up with each other. So group 3A is the same as 13, group 5A is the same as 15, group 7A is the same as 17, group 5A is the same as 15. So we're not going to trip you up by giving you the wrong sort of match between those. But if you look again back at choice C, which is the one that we've been sort of focused on because it has the right element in it, 7A17, is that the correct group number for nitrogen? Well, if you go to the periodic table, you will see that nitrogen is here in group 5A. So these again are the numbers that are given in our periodic table, or the A and B numbers. Nitrogen is 5A, and then the numerical value for that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 would be the numerical way of indicating that. So the correct answer, if it was nitrogen, should be group 5A or 15, not 7A or 17. So that answer choice can't be right because it has the wrong group number listed. So that's why none of the above is the one that should be correct. Now again, it requires you to look closely at the answer choice, not just find the element and the configuration that match, but also look at the group number. It also requires you to pick none of the above, which is sometimes psychologically difficult to do. But that's going to be the correct answer here, is none of these, because the group number for nitrogen was not stated correctly. All right, so that takes us to the end of this week's homework review. A lot of conceptual stuff, most of it all related to periodic treads and position on the periodic table, but a lot of little things in this chapter, a lot of things that sort of add up on each other. So if there's anything that's not clear about chapter 2, we've had 2 assignments on it now, but I'm still happy and available to go over anything that you want to go over with chapter 2, because we are going to be finishing chapter 3 very soon, and that's going to be the last chapter that's on our first exam. All right, so I'll see you guys in class later today, and if there's any other questions, please let me know.